So already you have in the recordings the solving of the previous problems. So we will start from problem 7. The girl, let me record. Oh, okay. The girl has mass m and center of mass at g. If she is swinging to a maximum height defined by theta equals to theta 1 equals to 60 degrees, determine the force developed along each of the four supporting posts, such as AB at the instant theta equal to 0. The swing is centrally located between the posts. So what do we have here? In this problem, you have a girl that is swinging between uh, a certain maximum angle and the vertical. The initial angle theta is equal to 60 degrees. And it's starting from rest at this position. So the velocity Vg at state 1 is 0. Then the girl will leave itself to swing around the vertical position. So in this case, we have variation of velocity as it is moving because the potential energy will be converted to kinetic energy. And we want to determine in particular when it is at theta equals 0, what will be the reaction at the support? Okay, this is the question. So first, to do the analysis, if you want to determine the support reactions when the girl is at this position, what should we do? What should we take as system, do you think? What do you suggest to do here in order to find the reactions at A and B? So here you have supports, okay? For these supports, how will be the force in case you know that AB is a two-force member? What do we mean by two-force member? When we neglect the mass of a certain rod, and we have only two forces acting on it at A and B, these forces, in this case, if you want the forces developed at A and B will be along the rod. So this means that the support reaction here will be along AB. And since you have four legs, so you have two from this side and two from the other side. So if we call this point here C, then we will have 2RB from this side and 2RC from the other side. And you can see that by symmetry, when the girl is at this position at 0 degree, you have symmetry in your figure. So you can say that in this case, RB will be equal to RC when theta equals 0. So for theta equals to 0 degrees, I have that RB is equal to RC due to symmetry. So this is because of symmetry. And now the second step is to try to find what equation to use to get RB and RC. So since RB and RC are applied on the legs, okay, so we can take as system to get RB and RC, we can take the four legs as system. If you take the four legs as system, then what will be the external forces? We said that the weight of the legs is negligible. This is why we can say that AB and AC are two force members, and therefore the forces will be transmitted along AB and AC. And they are connected, the legs are connected through pin A, which is subjected to what? To the action of the cable. So now, if you take the legs as your system, the external forces will be the reactions at the floor level and the tension T in this cable. T. So in order to solve for the reactions, we should get what is T. So this is the strategy here. We get the tension in the cable when theta equal to 0. Then once we find T, and we will find T from the girl analysis, we will see how. Once we find T, we can apply for the legs the static equilibrium relations because the legs are in equilibrium. So you can take, if you take the legs as system, for example here, you can write sum of y equals 0 and sum of x equals 0. Along x, you don't need, the x equation will not give you anything new because you already used the symmetry. From symmetry, you got that RB is equal to RC. This result is also, you can find this result also if you do sum of x. Because if you project on x, the x component will cancel out because you have 2RB times cosine this angle. Okay, or if you want, it's sine phi because this angle here is phi. So the angle of RB with the horizontal will be pi over 2 minus phi. So if you project on x, you will have 2RB sine phi minus 2RC sine phi equal to 0. So you will get RB equals to RC, which is the conclusion of symmetry. So here what will give us a relation with T is sum of y. Just let me check your chat. Someone is asking a question. Yeah, just why 2RB? Because you have 4 legs, okay? You have 2 legs from at the left side, and you have 2 legs at the right side, okay, for all?
Yes, Dr. Bashir.
Okay. So now, to get RB and RC, we will do sum of y equals 0. So if we write sum of forces on the legs along y equals to 0, this equation will give us, since we said that RB equal to RC, so you will project, you can replace RC by RB. So you can say that you have 2RB cosine phi, because look, the angle of the reaction with the vertical, this is the vertical, the angle is, as you can see here, is phi. So to project on y, you should multiply by cosine of phi. So you have 4 RB cosine phi minus the tension T minus T, which is the force in the cable, developed in the cable, equals to 0. So this will give you the value of RB function of T. So you can deduce that RB can be calculated as T over 4 cosine phi. The angle phi is given, so we still need to find what is T. Okay? Now, how to think about T? T is the tension in the cable, and the cable is connected to the girth. Okay? So let me erase now this. So now the issue is to calculate the tension in this cable. And you know that this cable is attaching A to the girl. So now if I take the free body diagram of the girl when it is at this position, at the vertical position, what are the forces acting on her? We have the tension.
The weight and tension.
Yes, we have the tension, and what also?
The weight.
Exactly, and the weight. Okay? Step. Who will tell me how can I find the tension? Which equation I should use for the girl to get the tension T? When you want to get a force, you think about which law?
Sum of forces.
Very good, sum of forces. What type of system you will use? UNUT, rectangular coordinates? What do you suggest? Look, if we use rectangular coordinates, let us say we want to use rectangular x and y, okay? Let's say this is x and y. Do you know what is a y?
Oh no, we use here we use the شو اسمه؟
Yes,
normal,
yes,
normal
exactly.
and tangential.
Yes, very good. Normal tangential. Because as I told you, whenever you have circular motion, okay, use normal tangential coordinates. Why? Because you will take the advantage that you know an. Because in normal tangential coordinates, the expression of an is given by v square over the radius of curvature. So here you are moving along a circle, and this circle is characterized by a radius equal to the length of the cable. So rho is equal to L. And therefore, if you want to get an, all you have to do is to find the velocity v at the vertical position. Okay, so if I am able to get v at the vertical position, I will be able to calculate t, because I can write then that if I put ut un at the vertical position, in particular at this position, how is ut? Ut is always tangent to the path. So since it's a circular motion, ut is always perpendicular to the radius. So at the vertical position, the radius is vertical because the radius is along the cable. So ut, which is perpendicular to the radius, will be horizontal, and un will be perpendicular to ut, directed towards the center of rotation, which is A. So this is un. And therefore, since my tension is along un, the equation that will give me T is sum of forces along the normal equals to plus T minus W equals to MV. I will call it V2 if you want, because we said that V1 here is 0. So I should find what is V2 here to be able to calculate AN at this position. Okay, so it's M times V2 squared over rho, where rho is the length of the cord. So now I know the weight, I know L, I know M. So to get the tension, I still only need to find V2. Okay, now how we will calculate V2? What can we use in a simple way to get V2? Which equation? Which theorem?
The conservation of energy.
Very good. You can do or conservation of energy or work and energy. Both will work here. Because why you can apply conservation of mechanical energy in this problem? What are the two forces acting on the girl? You have just the weight and the tension. Now, what is the force of the tension? What is the work of the tension between position 1 and 2 as you are swinging? Very good, 0. Why it's 0? Because at any position, exactly. Because at any position, your tension will be perpendicular to ut. So it's perpendicular to motion, and therefore it will not produce any work. So we can say that the work of T is equal to 0, since it is always perpendicular to motion. Okay, so the only force doing work here is the weight, and therefore, because it's a conservative force, so knowing that the weight is a conservative force, then we can apply the principle of conservation of mechanical energy. Or also you can say directly, I want to apply work and energy. Work of T is 0. Work of weight, I know the formula. So both methods, of course, will give me the same result. Okay. So let us do, if you want here, the work conservation of mechanical energy. Whenever we want to apply conservation of mechanical energy, we should define the potential function we have here. Here, since only the weight is doing work, so we only have the gravitational potential. For the gravitational potential, we should select a reference. We can take, for example, here, the most convenient choice will be this one. But whatever is your reference, it will not affect your final result, because at the end, what you care for is delta y, the variation of position. So the selection of reference will not affect your result. Whatever you take the reference, at the end, delta y will be the same. Okay, so here, if I consider this is my reference line or datum, then my potential will be negative, because we said that the gravitational potential will be positive above the reference and negative below it. So initially the girl is at this position, it is below the reference, and it is at a distance of, from the reference, how we calculate this distance here? It's equal to what?
Pythagorean.
No, because look, you have this angle here. This is theta, okay? And you know this length L. So just you have to project, okay? So this angle will be equal to this one, since they are alternating angles. So this height will be L cosine of theta, okay? And now we can say that the gravitational potential Vg at state 1 is given by, since we are below the datum, it's negative, so it's minus m times g times L cosine theta, okay? And concerning the kinetic energy, so T1 is equal to 0 because we are starting from rest, okay? Since we start from rest. Now, the second position of interest is the vertical position. When I am at the vertical position, what will be my gravitational potential at this position? Vg
Minus mt times 2 times L. يعني.
times L, very good. Because the vertical distance now from the reference will be equal to the length of the cable, because my cable is in the vertical position. So this is L, and therefore I can say that at position 2, we have that V gravitational at state 2 is equal to minus mg times L. And concerning T2, T2 is unknown. It will be function of V2. T2 is equal to half m times V2 squared. So now, all I have to do is to replace in the equation of conservation. The conservation of mechanical energy will give me that T1 plus V1 is equal to T2 plus V2. And in this equation, what will be the only unknown? So if you replace all your parameters, the only unknown is V2. Since you know theta, you know L, you know mg, so V2 is the only unknown. Therefore, you can get V2 from this equation. And once we find V2, as we said, we replace into Newton law to get the tension. Okay? Any question on this?
يس دكتور انا عندي سؤالين.
Yes.
بس اليو تي هي دايما بناخدها 90 degrees counter clockwise لليو ان.
لا انتبه انت ما خصك هون، ما خصك clockwise و counter clockwise. Look, هعطيك example. Okay? If this is a girl. When it's swinging like this, يعني بس when it's going from left towards right, كيف حتكون اليو تي؟ UT always follows the velocity. يعني in this case, UT at any position is like this, directed towards right. وقت توصل الجيرل للماكسيمم position هون بدها ترجع تنزل. ساعتها UT بتقلب مع الجيرل. So UT will always follow the velocity. It's not if you want a vector that is always going in one direction, it follows the velocity. So when you were moving like this, UT was going from left towards right. When you change your stance, it will change with you. Okay. On the other hand, UN always directed towards the center of curvature. يعني تخيل أنت وقت تكون in this from this point to this one, when you pass by this point, حتكون UT لتحت. UN always directed towards A. Perpendicular to UT. بينما when you go in the reverse direction, what will happen? UT حتبرم بس UN حتضلها. يعني when you pass by the same point but in the opposite sense, UT will be opposite but UN will be the same. اوكي
اوكي ثانك يو. بعد سؤال ثاني بس عملنا ال conservation of energy، ليش ليش اخذناها minus WY مش البوزيتيف دايركشن اخذناها لفوق؟
لا لانه انت look whenever you take a reference بس تكون انت below the reference يعني negative potential و above the reference يعني positive potential. هلا هون انا دغري عملتها. اذا بدك تحط y axis you can take it. if you take y positive upward شو بتكون الاكسبريشن للv للgravitational potential؟ بتكون plus mg times y. اوكي ساعتها if y is positive this means that you are above the datum. This is why your potential will be positive. وانت in this case since you are below the reference يعني your y is negative ساعتها you replace y by minus L cosine theta و minus L. إذا أنت أخذ y downward positive يلي بيقلب هو بس الساين هون يعني v بتصير minus mgy أوكي بس your potential value بتضل هي ذاتها. يعني أنت بس تكون تحت الريفرنس إجباري تكون v negative in both cases. أوكي
لو اخذين الديتيم تحت كانت بتكون بوزيتيف.
مزبوط لو اخذين الديتيوم تحت بتكون v positive. بس وقت ناخذ الديتيوم فوق وانت your girl is below the datum wherever is y يعني اذا y positive up او y positive down this will not affect the sign of your potential. It will just affect the sign بالاequation. But at the end in both cases v will be negative below the datum.
Okay, thank you.
Okay. If it's not clear I can give you a numerical example.
لا واضحة مش الحال. Thank you.
Okay. Another question.
بس عندي problems.
Sorry, I cannot hear you. Can you please repeat?
عندي بس question problem
أكيد. Which one?
3.
Just tell me the number. Problem 3?
Yes. أنا إنه الفيلم عم تظبط.
Look, your voice is lagging. Can you type your question in the chat, please? Yeah, I will wait for you. Type it in the chat.
Doctor, can you hear me?
Yes, now it's better.
Okay. كنت عم أقول إنه الفي ما عم تزبط معي، ما عم تطلع 10.4.
طيب الميثود you understood the methods I did يعني بس قصة calculation. You use the same method.
Yes, نفس الأرقام ما عم تطلع 10.4.
انتبهت إنه بالساين بده يكون هيدا ال AX in radian مش in degrees. هن already هن حاطين لك A in degrees per meter. لا لكن in degrees يعني A is 10 يعني sin let's say 30. Look if you want بعت لي your solution by WhatsApp and I will tell you what's your problem. Okay?
Okay دكتور.
يعني أنت فهمان الإيكويشن بس قصة calculation.
Yes, exactly.
Okay, no problem. I will check what's your mistake. Okay?
دكتور أنا كمان جربتها بذات الميثود طلع لي 6.8.
هلا هن اوقات بالسوليوشن مانيوال اوقات بيعملوا calculation errors يعني it's possible. I will check it for you. Okay?
Okay, merci دكتور.
Another question on the previous problems. حدا عنده question on the previous problems?
دكتور كان بدي أسألك إذا فيك بس ترجع تشرح شوي صغيرة exercise 6.
6, yes, yeah. Sure. Okay. The escalator steps move with a constant speed v. If the steps are of height h and length L, determine the power of a motor needed to lift an average mass m per step. There are n steps. Okay. Here the whole idea here is first when you want to lift any object, you are opposing what?
Weight.
Yeah, exactly. You are opposing its weight. Okay. So when you want to determine what is the power needed to lift each step, okay, so let us think first per step, and then we can multiply by n to get the power needed to lift n steps. So if you want to lift just one step, you should overcome its weight. Okay, so the power is opposing the weight. So this is why, by definition, you know that to calculate the power, you do F developed dot velocity dot V. Okay, the force you are putting should oppose the weight. This is why here F is equal to the weight in the vertical direction. Okay, and since your velocity is inclined, then you should do the projection. Okay, so look, this is your V, this is your velocity, and you are developing a force set to overcome the weight, a force F. So once you want to, where F should be equal just to the weight to be able to lift the escalator. So here, when you apply the formula of the power, F dot product V, you should know what is the angle between your velocity V and your force F. To get this angle, okay, this angle is equal to here the step angle. So this is why they gave you the dimension of your step. So for each step, you have a height h and you have a length L. Okay, so the velocity will be along this line, and therefore the angle theta to calculate. So here, if you want, theta is not this one, it's here, because نحن عم نشتغل على theta with the horizontal. Okay, so this is why when you want to do the dot product, you do cosine this angle. This angle is pi over 2 minus theta. Okay, so when you want to do the dot product, you will write that the power per step is mg times v times cosine pi over 2 minus theta, and cosine pi over 2 minus theta is equal to theta. Now, how to find the value of theta? As we said here, the value of theta is determined by the dimensions of your step. So if you look at the figure here, V is along this line, and this line can be determined by the slope, which can be calculated as tangent of theta is h over L. So once you get theta from this equation, so theta is tangent minus 1 h over L, you can then replace theta into the equation of power to get the power to lift one. So the power to lift one step is mg times v sine theta, and for n steps you multiply by the number of steps, which is n. Okay?
Yes, doctor. Thank you.
Welcome. Any other question on the previous problems? Okay. So let us continue. Each of the two elastic rubber bands of the slingshot has a non-stretched length L. If they are pulled back to the position shown and released from rest, determine the maximum height the mass M will reach if it's fired vertically upward. Neglect the mass of the rubber bands and the change in elevation of the mass while it is constrained by the rubber bands. Each rubber band has a stiffness scale. So in this problem, we have rubber bands that act like springs, if you want. Okay, so these rubber bands act as springs, elastic springs. They gave us their unstretched lengths. And initially, look what we are doing. We are stretching them. And we can calculate what is their length. So this is L, if you want, at state 1. Okay. So at state 1, my springs are, or my rubber bands are stretched. They are stretched to a certain length L1. So in order, you know that whenever we have a spring, then we can determine the work, or we can use, in case all forces are conservative, we can use conservation of mechanical energy. So here, let me draw the figure. The initial position of the bands is like this, and this is the mass that we want to pull. Okay, so here we are firing it vertically upward. So we are giving it a certain initial, if you want, it's initially at a velocity of 0, but because we have stretched the bands, we are having energy in the form of elastic energy. And once we leave the mass, the elastic energy will transform into potential energy to rise it upward. Okay, now the main forces acting on our system will be what? We have the spring forces and we have the weight. So we can say that in this case, since all forces are conservative, spring and weight acting on the small mass, then we can apply conservation of mechanical energy. Now, we should define two states. The initial state, state 1, this state is characterized by a velocity of 0 because we are giving initially, it is fired from 0, from a velocity of 0. So T1 is just equal to 0. You can just say this is 0 because it's starting from rest. And concerning the potential energy, we have here both elastic and gravitation. Okay? Now, you can, for gravitational energy, you should take a reference. So it is a good idea to take the initial position as reference. Because if you take the initial position as reference, V gravitational 1 will be just equal to 0. And you still just need to evaluate what is the elastic potential at position 1. Can you tell me how we calculate the elastic potential? What should we do?
We find
Yes, we have two springs, okay? So it's 2 times the elastic potential in each spring. And what is the formula of elastic potential for each spring? Who remembers? V elastic, yes, exactly. It's half K delta L squared, okay? So we can say that V elastic at state 1 for each rubber is half K delta L1 squared. But since we have 2 rubber bands, then we should multiply by 2. Okay, since here, due to symmetry, as you can see in this figure, due to the symmetry, the 2 rubber will have the same length L1, and they are both characterized by the same unstretched length L, so they will have both the same delta L value. So we can just here multiply by 2. When you multiply by 2, 2 can be simplified because we have times 2 over 2. So we can say that V elastic at state 1 is just K delta L1 squared. Now, how to compute delta L1? Delta L1 always can be calculated as the total length of the spring or rubber, which is L1 here at state 1, and we should subtract from it minus the unstretched length, which is L. So if we look at our figure, to get L1, we have the following distances. We have this distance is A. We have this distance is B. So we can apply Pythagorean theorem to get L1. Since L1 is the hypotenuse in this right triangle, so it's given by radical of A squared plus B squared. And A and B are given here. This will allow us to calculate the value of L1. Once we get L1, we should not forget to subtract L0, which is here 200 millimeter. Then we get the value of delta L1. Okay? Now, at the final state, what will be the final state we will take in this problem? If you read the question, what they want you to find? They want you to find the maximum height the mass can reach. Because they are asking for the maximum height, then you state 2, you should select state 2 as the position where you reach the maximum height, H maximum. What is the characteristic at state 2? When you reach the maximum height, what will happen?
E equals to 0.
Exactly. So V2 will be 0. Because if I reach the maximum, then I cannot go upward anymore. This means that my velocity will reach 0 and I will change my sense of motion. So then if I wait some time, I will see that the mass will go downward again. Okay? So at this position, I know that V2 is equal to 0. Concerning the elastic potential, do I still have an elastic potential at this position? The elastic at state 2?
Yes.
Why? Why yes?
We're considering this mass. Is it still attached to the spring?
No, it's not.
Okay.
بس أنا
فإذا
only
no, we
one.
don't.
No. هلا look, هي why it's little bit confusing for you. في عالم بفضلوا يحلوها in steps. يعني some people say let us divide the problem into 2 steps. Step 1 بس كان عندنا ال V0 وعندنا maximum elastic energy. هلا بس نكب الماس شو حيصير؟ حتصير السبرينج يرجعوا على unstretched position. اوكي؟ يعني كل الالاستيك energy حتتحول ل which type of energy؟
Potential energy. Gravitational potential energy.
قبل يعني just انا اذا بدكم من بعد ما كبها دايركتلي بكون اعطيتها a certain velocity لانه once كبيتها بكون حولت اذا بدكم هالالاستيك energy اللي كانت موجوده ل a certain kinetic energy and this kinetic energy will then be transformed into potential تطلع. يعني هي شو الايديا؟ اول شيء كان عندنا بس elastic energy وقتها كبينا البول شو صار؟ تحولت هالالاستيك انرجي بسبرينجز عطت initial velocity للماس. يعني انتم الماس ليش حتطلع لفوق؟ لانه عطيها وقتها فلتناها اعطيناها بوش. اوكي؟ اعطيناها a certain velocity وصارت البوتنشال انرجي تبعها الالاستيك انرجي تبعها صارت 0. يعني اذا بدكم نقسم 1 2 3 فينا نحط انه نجيب what is velocity 2 directly after it is fired. يعني من بعد ما كان من بعد ما صاروا الرابر unstretched. اوكي؟ we can get the value of V2 وبيرجع من 2 ل 3 تتحول الكايناتيك into potential. بس ما في لزوم نقسم ل 1 2 3 لانه هن ما سالونا what is the velocity given to the ball directly after it is fired. لا هن بس سالونا the maximum height. يعني we can directly apply between just initial and final state. Okay? But at the end you can divide it into steps and you will get same results بس بتكونوا عملتوا more calculations. Okay? So you can directly apply between the state where it has no velocity لما كان بعدنا لقطينا بإيدنا. لأنه أنتوا وقتا كنتوا لقطينا بإيدكم بس كان في elastic energy. بس تفلتوا إيدكم شو بيصير؟ elastic energy بتصير kinetic energy. فبتتحول من elastic بصيروا rubber بصير unstretched وبيكون عطي velocity لل ball. And then kinetic energy will be when as you go upward, this kinetic energy will be transformed into potential energy. Since here they didn't ask you what is the velocity after we remove our hand, ما في لزوم تقسموا 1 2 3. You can directly apply from 1 to 3 because this will give you the final answer in just one step. Okay? Any question on this? So if you want, let us see the details here together. So here they just applied between the initial and final state. So therefore, the initial potential energy was converted into the potential elastic energy was converted into potential gravitational energy from 1 to 3. Okay? If we want to add a question, we can just add what will be the velocity just after firing, yani after removing the hand. Then you can divide them into steps 1, 2, and after. Okay?
Doctor, could you just repeat what you just said?
Yes, I will. Okay, here you have steps in your problem. In a first step, you are holding the mass with your hand. When you hold the mass with your hand, does it have a velocity? Here. كانت initially velocity 0 لأنه كنا حاطين our hand on the ball. And in this case, we had a certain maximum stretching of your rubber. مظبوط؟ طيب. Now, what will happen when you leave when you leave the particle شو حيصير؟ حتضل إذا بدكم البول in contact مع الربر for a small distance. هن قالوا لكم neglect this distance. يعني in the problem, look at what they told you. They told you neglect the mass of the rubber bands and the change in elevation of the mass while it is constrained by the rubber bands. شو قصدهم بهالجملة؟ يعني نحن إذا بدي أرسم لكم initial state, this is the initial state. Okay? كانت الماس at this level. We had in this case V0. V is equal to 0 at this position. And the kinetic energy, the potential energy is maximum. Okay, يعني V elastic هي half K delta L1. Okay, what will happen when you remove your hand? When you remove your hand, the stretching of the spring حيخف لحديت ما توصل للposition لما يكون unstretched. Okay, so if you want بس يصير الرubber at a certain location here ويصير unstretched ببطل في elastic potential بس بيكون تحول هالاlastic potential energy to what? To kinetic energy. يعني هون at this position بتصير ال V elastic 0 وبتكون تحولت ل هلا هي in real case حتتحول ل V gravitational لأنه في small variation in altitude. هيدي كتير صغيرة بس. Let's say إذا سميناها small h إذا بدكم or small x بما إنه عنا h من قبل. شو حيصير من هالposition من 1 ل 2؟ عنا change in elevation x بس هن قالوا لنا neglected يعني هيدا change in elevation is very small that we can consider it as negligible. فوقت تروح من position 1 ل position 2 mainly elastic energy حتتحول ل which type of energy? Kinetic energy. يعني at position 2 عندي بتصير T2 equals to half m times V2 square. يعني تحولت potential elastic energy ل kinetic energy neglecting هال small change in elevation. إذا بدنا ناخذ ال x into account كمان بيصير بدنا نكتب إنه half k delta L1 square اللي هي ال initial elastic energy. أوكي حتتحول part ل kinetic energy اللي هي half m V2 square. And a certain part حتروح potential يعني plus mg times x. Okay? بس بما انه هن قالوا لنا انه x is negligible يعني we can neglect this small term okay compared to this one. فمينلي at an initial stage حتتحول كل ال potential energy of the rubber to elastic energy to a kinetic energy. Once وصلنا لهال position 2 خلص صار spring unstretched ما بقى يعمل effect. من 2 ل 3 شو رح يصير؟ It will move upward, the mass will move upward, and as it is moving upward, its velocity will decrease and its height will increase. Therefore, the kinetic energy will be transformed to potential until reaching the maximum height. نحن اللي عم نجيبه هو ال H maximum. Okay? So to get H maximum, you can apply conservation of mechanical energy between 2 and 3 after getting V2. بس أنا اللي عم أقوله كنت ما في لزوم نعمل 2 steps يعني بدل ما نقسمها 1 2 3 since they didn't ask for V2 ما قالوا لنا what is the velocity of the mass when it will leave the rubber. Okay? Just طلبوا منا ال maximum height. So you can directly apply between the initial and final step. Okay? Is it clear?
Yes, thank you doctor.
Okay.
دكتور
Yes.
هلا نحن بكل هيدا الشابتر we're assuming انه ما في friction ما هيك؟
Look, مش we are assuming ما في friction. إذا في friction في problems فيهم يكونوا friction. هلا بنعملهم. إذا في friction you cannot apply conservation of mechanical energy. You apply the principle of work and energy. Okay.
Yes.
This is an
Okay.
example here. Exercise 2 is a shifty. If you watched the recording, you have it in problem 2. And if you want, I can re-explain it if you have a problem with it. So here, this is an example where you have friction. When you have friction, you cannot apply conservation of mechanical energy. You just apply the principle of work and energy. And for example, here, you have the force F. To get its work, you should project it on the direction of motion. So it's F cosine theta. And since theta is variable, إذا بدكم خليني أعملكم إياه يلا I will solve it again for you. So the collar here has a mass m and is moving at speed v1 when x is equal to 0. If a force F is applied to it and the angle theta is varying in a way that theta equal to a times x, where theta is measured in degrees, determine the speed of the collar when x is equal to x1, knowing that the coefficient of kinetic friction between the collar and the rod is equal to mu k. Okay, so here, for example, you have a collar that is moving along x. The forces acting on the collar are the weight, the normal, force F, and the friction. Since they gave you the kinetic friction coefficient, this means that you have friction between the collar and the rod. And this friction is equal to mu k times n. And in order to get the friction, you need to get n. To get n, you just have to apply Newton's law along y. So here, this is y-axis, let's say. This is y, this is x. Okay. You have that sum of forces along y is equal to 0. This will give you that the normal reaction is equal, you should let us project on y. So we have plus n minus weight, but don't forget here that to account also for the projection of f. So if you project f on y, you have minus f sine theta. So minus f sine theta equals to 0. So this will give us that the normal n is given by w plus f sine theta. Okay. Now, since theta is variable in this problem, pay attention whenever you have variable forces. So theta is given here function of x. Theta is equal to a times x. Since you have variable forces, variable angle, then when you want to predict the work, you should do integration. Because if you remember, when we define the work of a force, we said that du is f dot dr, where dr represents the displacement. Okay? So here, for example, the forces doing work are only F and the friction, because the weight and normal are perpendicular to motion. So just you have the work of F and the work of friction. But you cannot here apply conservation of mechanical energy because you have a friction force. So you have dissipation of energy. Therefore, if you want to write the work of the principle of work and energy, you know the initial velocity, v1. So you can write that half m v1 square plus, we should account for the work of F, big F, plus the work of the friction, we call it small f, should be equal to the final kinetic energy. Here they are asking for the speed for a certain, when you move a certain distance x1. So we need to find what is v at x1. Let's call it v2. So v2 is unknown. We should find. Okay. So now when you write this theorem, v1 you have it, you replace by a. You just still to get what is the work of big F and what is the work of friction. Since the angle of projection is variable, you should perform integration, because you know that du is F dot dr. So if I want to take for the work of F, the elementary work is F. When you project F on dr, what do you get? You get F cosine theta dr. F cosine theta. dr here is dx because your coordinate is x. So it's F cosine theta dx. And since theta is given function of x, theta is equal to ax, you will perform your integration with respect to x. So the total work, to get the total work, you integrate over du. So integral du is equal to integral from position x1, from 0 if you want. Initially it's at x equals 0 to x1. Okay? Since theta is variable here, we cannot take it outside of the integration. We should perform a normal integration. So you replace theta by a times x. And you know that integral of cosine theta, okay, is sine theta. But here, since you are integrating with respect to x, you should pay attention to divide by a. So the integral here will give you f sine ax over a between your boundaries. Your boundaries are from 0 to x1. So you apply this integration between the two boundaries and you get the work of F. Now to get the work of the friction, you should perform in a similar way, because also your friction is variable. Why it's variable? Because if you look at your normal equation, your normal is function of theta and theta is function of x. So just here also, to determine the work of the friction, you should say that the elementary work of the friction, small f, is equal to f, small f vector, dot dr. And here, since your friction is opposing motion, when you do the dot product will give you what? The angle between dr, which is dx, and the friction is 180. So when you do the dot product, it will give you minus the friction force times dx. And then to get the total work, you should integrate, because F is not constant. If F was constant, you just say that the work of friction is minus F delta x. But since F is function of x, like a big F, then you should perform integration to get the work. Okay? So whenever you have friction, you apply principle of work and energy.
Doctor, question.
Yes.
Can we calculate the work of the friction by equals minus delta mechanical energy?
Yes, I see what you mean. You can, look, you have several ways you can write. You have two theorems. You can write the conservation, you can write the work and energy, which is T1 plus sum of work between state 1 and 2 equals to T2. And the theorem you are talking about is, the other version is T1 plus V1 plus sum of work of non-conservative forces. Here, for example, in this problem, you have the non-conservative forces here will be both friction and F. So here in this problem, okay, you will not apply this theorem لأنه ما عندك يعني أصلا conservative forces ما عندهم work. يعني أنت عادة بس يكون عندك weight وspring بتقول إنه في conservative forces. ساعتها إذا كان في friction مع الويت والspring, you can apply إنه T1 plus V1 plus sum of work of non-conservative forces equals to T2 plus V2. يعني معك حق. ساعتها فيك تقول إنه sum of work of non-conservative forces هو الفاريشن هو إذا بدك minus delta mechanical energy. لأنه هي سوري هي delta mechanical energy اللي هي T2 plus V2 minus T1 plus V1. بس بهذا البروبلم it's not applicable لأنه أصلا كل الفورسز تبعك non-conservative. يعني ال F is not conservative والفريكشن is not conservative. يعني هون ما لها معنى تستعمل this theorem لأنه أصلا ما عندك potential ما عندك هون you cannot define potential energy. اوكي بس لو كان في problem في بس weight وspring وفريكشن then yes you can say إنه إذا بس الفريكشن هي non conservative بتقول إنه ال work of friction هي delta of mechanical energy. It's right.
اوكي ميرسي دكتور.
Okay. Any other question? Okay, so let us continue. The color of weight W is released from rest at A and travels along the smooth guide. Determine its speed when its center reaches point C and the normal force it exerts on the rod at this point. The spring has a non-stretched length L and point C is located just before the end of the curved portion of the rod. So in this problem, you have a color moving between A and C, and you want to determine what will be the normal force at point C. This is the question. So in general, the problems you might have will combine several chapters. So you might need to do Newton law, so use chapter 13, and use work and energy for velocity, because you know, especially in UNUT frame, to get AN you need a velocity. So this combination, you can see it in a lot of problems. So the question is to get the normal reaction at C. This is why the first step is to draw the free body diagram. So when your color will reach point C, the forces acting on it are the weight, the normal reaction of the guide, and the spring force. Okay? Now, the spring force is always along the spring. So whenever your spring is at this position, then the force will be directed along it. So at C, the spring force is like this, okay, along the line of the spring. And this is my free body diagram. Okay, I can get the angle theta if needed. We will see if we need it or not. So I can find it simply by using geometrical law, because we know that this distance is h. We know that this distance, let's say, is L. So we can calculate the angle theta if needed. Okay. Now let us try to think together. The problem is to find the normal reaction at C. To find this normal, we should write a Newton law. Now, to write a Newton law, we should use a frame. Since the color, when moving from A to C, is moving on an arc of circle, directly think about using normal tangential coordinates. So if you will use normal tangential coordinates, you have that the tangential coordinate first is tangent to the path. So at point C, it will be along the vertical, because as you can see here, at C, the radius is horizontal and UT is perpendicular to the radius. So at this location, this is UT, and UN always is perpendicular to UT, directed towards the center of curvature. So at this position, this is UT, and this is UN. Okay, and since I want to determine N, I need to project on UN. So if I project on UN, I write that sum of forces along UN equals to MAN. I can replace AN by velocity at C square over the radius of curvature. So it's M times VC square. Now concerning the radius of curvature, it is the radius of the circle. Since you are moving on a circle, the radius is L, okay? So I will do MVC square over L. Now, let us project on UN. What do we have? We have the normal plus NC. The weight is perpendicular to UN, so no projection. We need to determine theta in order to project the spring force, okay? So how to calculate theta? If we go back to this figure, this is theta here. Calculate theta, we simply say that knowing that this distance is L and this is H, so tangent of theta is L over H. So we can get the angle theta. Okay, and then we have NC plus the spring force at this position, Fs, times sine theta equals to mvc square over F. Now let us see what do we know in this equation. First, NC we don't know it, we want to calculate it. Theta was calculated. Concerning the spring force, whenever you have a spring, you can calculate the spring force by K times delta L. And since we are interested at position C, so we should find what is delta L at point C. To get delta L at point C, it's very simple. The method always is the same. I find what is the length of the spring at position C, and I subtract from it the unstretched length. Okay? So here, at position C, LC is given by using the Pythagorean theorem. So LC is given by radical of, you have this distance is h, this distance is L, so it's radical h square plus L square. Okay, this will allow us to calculate the value of LC. Now once we have LC, delta L at point C is given by LC minus L0. Now the unstretched length is given to be, if you go upward little in the forgiven, they said the unstretched length is big L. So all you have to do then to obtain delta L C is to subtract from radical h square plus L square, you subtract L. And since the stiffness is given, then in this way you can calculate Fs. Then the only remaining unknown is Vc. So if you can get Vc, you can replace back in this equation to find the normal at C. So now the idea is to get this. In order to get the velocity, we can think about the easiest way, which is or work and energy or conservation of mechanical energy. Why here we can apply the conservation of mechanical energy? Because you have that the normal is always perpendicular to motion, so no work. And you still have only two conservative forces, which are the weight and the spring. And since these forces are conservative, then we can apply the principle of conservation of mechanical energy between the initial position, which is at A, and the final position at C. Okay. Now, if you want, I will add a question. If in case we have friction, what should we do? Okay. Let us solve it with friction so that it will become more complex and you will benefit from it. So, in case you have friction in this problem, if I take any position, at any position, I will have the normal reaction. I will have the friction that is opposing motion. This is F. And F, then they should give me, if we have friction, they should give me mu K. So F will be equal to mu K times N. And I have, of course, the weight and the spring force. Now, in this case, in case they give me this scenario, okay, then I should, to find the work of friction, I should perform an integration. Why? Because look, the normal, as we have seen together, is function of theta. And if the normal is function of theta, also the friction will be function of theta. And then you cannot say that we will apply the conservation of mechanical energy. You will say that we will apply the principle of work and energy. Or, as your friend said in the previous problem, we can use T1, so T at A, plus V at A, total potential energy at A, plus the work of the friction, since it's a non-conservative force, okay, equals to kinetic energy at C plus potential energy at C. So if you want, work of friction here will be equal to delta of mechanical energy. Delta mechanical energy. Okay? So this is equivalent also to write the principle of work and energy. So because if you write work and energy principle, you will have that TA plus work of friction plus work of weight plus work of spring equals to TC. Okay? And we have seen together, if you remember, when we derived the potential energy, we have seen that we can replace the work of the weight by VA, V gravitational at A, minus V gravitational at T. And also for the potential, for the work of spring, also we can replace it by the elastic potential at A minus the elastic potential at C. So this is why the two are equivalent. So if you rearrange your terms here, you will go back to this relation that TA plus VA. V represents the total potential, including gravitational plus elastic, plus work of friction will give you TC plus VC. Okay? So in this case, just I should add the computation of the friction work. And to get the friction work, it is complex here. Why? Because as we have seen, N is function of theta. And also you have that friction is function of theta. So if you want to perform the work of the friction, you should integrate over theta. Okay, which will give you some complexity in the solution, but this is the procedure. But here, since we don't have friction, it's much easier. When you don't have friction, your equation will be restricted to conservation of mechanical energy, because delta mechanical energy will be 0 if you don't have non-conservative forces. And then in this case, the equation to apply will be TA plus VA equals to TC plus VC. So all we have to do now to get VC is to write the expression of TA, VA, TC, and VC. So let us do it together. First, since we are starting from rest, we can say that TA is equal to 0 because at A, velocity is 0. So it's starting from rest. Now, concerning the gravitational potential, V gravitational at A. Whenever you have gravitational potential, you should take a reference. And as I told you, you are free to select the reference you want. For example, you can take here the reference at A or at C, no problem. At the end, delta V will be the same. Okay, and the value of V will change if you change the reference, but delta V will be the same. And what I care for is delta V, because I will have always VA minus VC. Okay, so what is important for me is not the value of VA and VC, it's delta V. Okay, so if I take the reference at this level, then V gravitational at A will be 0. And concerning the elastic potential, V elastic at A, to get V elastic at A, I need to determine what is delta L of my spring at A. So V elastic is 0.5 times K times delta L at A square. Okay. Now, to get delta L at A is equal to the total length of the spring at A minus L0, the unstretched. If you go back to your figure, when we are at A, this is my spring. My spring will be like this, will be in the vertical position. Okay, and the total length of my spring will be this distance, which is H plus L. Okay, so if I apply at A, LA, I replace it by H plus L, and L0, I replace it by the unstretched length of the spring, which is big L, plus L minus L will simplify, and then I have that delta L at A is H. Okay, so I can say that V elastic at A will be simply 0.5 times K times H squared. Okay, so So we are done with the parameters at point A. Now we will determine what are the parameters at point C. Concerning TC, it is unknown, and this is what we want to find from the conservation of mechanical energy. TC is 0.5 times the mass times the velocity at C squared. We have that V gravitational at C, since our reference is at A and C is below the reference, so it's a negative potential. So it's minus mg times the distance. This distance is L. So V gravitational at C is minus mg times big L. And finally, for the elastic potential, V elastic at C is equal to half K delta LC square. And we have together already found what is the value of delta LC because we used it for the spring force here. Okay, so just you have to replace delta LC by LC minus L, and you get the value of the elastic potential. Okay, now by replacing in your equation, the only unknown in this case will be the velocity at C. So as you can see here, replacing back, the only unknown is VC. We can get the value of VC, and after getting VC, we can apply sum of n equals MAN to get the normal reaction. Okay. Any question on this?
يس دكتور عندي سؤال بس
Yes. Tell me.
بالفري بادي دايجرام
Yes.
النورمال على السي مش لازم تكون صوب الشمال يعني
النورمال على السي اوكي كيف بنعرف؟ look here you should you can do an assumption. فيها تكون على الشمال فيها تكون to the right. You know why؟ لأنه it depends on the value of fs. يعني أنت you can do an assumption تاخدها towards the right and you calculate. إذا طلعت لك positive value يعني مظبوط هي to the right. وإذا طلع لك negative value يعني هي to the left. But both scenarios are possible. You know why؟ لأنه it depends on the value of the spring force. اتفقنا؟ يعني حسب البالانس لأنه أنت بالآخر ال N is equal to if you get the value of NC هي half mv square minus fs sin theta. So it will depend على هالبالانس مين أقوى half mv square أو sorry it's mv square over rho. يعني أنت عندك N هي m vc square over L اللي هي MAN minus البروجكشن of fs لأنه بناخدها للتاني مان يعني minus fs sin theta. اوكي فهون it depends مين أعلى هيدا الترم إذا MVC square over L أكبر أو fs sin theta أكبر. اوكي so you should perform the calculation to make sure كيف حتكون NC. This is why you do an assumption. You can take it to the right and from your calculation إذا طلع لك positive result يعني مضبوطة your assumption. إذا طلعت لك NC negative يعني هي like
دكتور
yes.
مش نحن دغري فينا نعرف انه هي نص صوب اليمين لانه ال OB equals L.
لأنه OB equals L.
Yes.
وإذا OB equals L يعني أنت هون ما عندك stretching the spring. It will depend on the value of H. يعني أنا إذا بغير لك ال value of H كل شيء بيتغير لأنه أنت حتتأثر بال value of the velocity هون و of the spring force. يعني حسب هالcombination حتحدد لك يعني you can have a net a positive value you can have a negative value. It depends on VC and theta شو هن ال values تبعهم on VC and F spring I mean. اوكي يعني إذا بتلاحظ هون هيدي الإكسبريشن تبعك. This is your expression. Okay when you replace in NC as you can see is a function of VC and a function of H. يعني أنت فيك تلعب بهول البارامترز. Okay so depending on these parameters معقول تكون NC positive أو negative. Okay يعني فيك أنت تجرب تنقي a certain value of H تعطيك a negative value of N. يعني if you want to see how you can just change the parameters. يعني إذا بغير H كيف تتأثر ال VC وكيف تتأثر ال NC. You can draw plot curves إنه if H is varying what will happen with VC and what will happen with NC.
دكتور بس بالفيجر على اليمين هيدا
نعم.
ال 3 body diagram تبع الرod او
تبع
الكولر؟
هيدا ال 3 body diagram تبع الكولر، تبع هيدا البارت البوكس هون. this one هو ال 3 body diagram تبع البوكس بس يوصل على C here. اوكي. Any other question?
دكتور بس عندي بعد سؤال شوي. هو
نعم.
ما خصوش يمكن اللي عم ناخده، بس اذا طلعت هان بهالكيس الان سي مثلا بوزيتيف، اجباري تطعج الرد ولا فيها في كيس ما تطعج؟
الرد ما بتطعج، ما هي انت اذا بدك هي هيدي اكشن رياكشن. الرد از ريجيد منا ديفورمبل. اوكي. هلا فيك حسب اكيد يعني بده يكون الماتيريال تبعه يكون يتحمل هالفورس. كل ماتيريال عنده ماكسيمم كونسترينت. يعني يمكن يقولوا لك انه هالرد اذا بتحط عليها فورس اعلى من هالقد بتطعج، ساعتها you should avoid getting a normal reaction above this value. بس عادة بس يعملوا الديزاين بيكونوا حاطينها تتحمل هاي فورسز فما تطعج.
ايه بس انا ما فهمت انه هي الاف اس اذا عملنا لها بروجكشن على الاكس تطلع صوب اليمين، كمان اذا الان سي طلعت بوزيتيف صوب اليمين
لحظة
مش
بس
اجباري لازم تطعج؟
لا لحظة شوي. انتوا هون تبع شغلة. in this case انت ما عندك for the color moving عندك AT وعندك AN. ما عندك هون انه sum of x equal 0 مثل ما عم بتفكر او شيء. يعني انت عندك هون بهالبروبلم عندك acceleration عندك two components tangential و normal. اوكي. انت بما انه بس interested بالnormal value بالvalue of the normal reaction you can get what from doing sum of n you can get the normal. هلا انت الرود ليش ما حطيتها؟ لانه انت you are applying on it a force n بس ما هي supported. it's supported at a fixity. يعني اذا بتشتغل بالستاتيكس اذا بتشتغل على الرود الفيكسيتي هون will oppose the effect of normal reaction اللي عم يعملها الكولر فما بتطعج.
اوكي ثانك يو.
يعني it's supported here مش انه هي متروكه لحالها. اوكي. يعني you can بس using statics فيك تجيب الرياكشن. حتى هون يعني بما انه في fixity من الميلتين you cannot use simply statics بدك تعمل كمان mechanics of materials اذا بدك تجيب الرياكشنز على السبورتس. يعني it's complex.
اوكي ثانك يو.
يمكن بعد ما اخذتوا الكورسز بكره بتشوفون وقت يكون عندنا more constraints. يعني هون it's over constraint هيدي الرود ف you cannot get the external reaction. you need additional properties بالميكانكس of materials تقدر تجيب الرياكشنز.
اوكي
any other question on this? Okay. Another problem. The bob of mass m of a pendulum is fired from rest at position A by a spring which has a stiffness K and is compressed a distance delta. Determine the speed of the bob and the tension in the cord when the bob is at position B and C. Point B is located on the path where the radius of curvature is still R just before the cord becomes horizontal. So here, what do we have? First, at the initial stage, the ball is compressing a spring. Okay. عطينا انه initially the distance, the value of delta. Just let me check what is A here. Okay. So they said that it is compressed a distance delta. يعني delta هون هي compression of the spring. So since your spring is initially compressed يعني في elastic potential energy. يعني at the initial state we have the ball is compressing the spring. Before leaving the ball يعني كانت velocity zero أول شيء. كنا حاطين البول على السبرينج وفلتنا السيستم. Once we release the system what will happen? elastic energy will be converted into other types of energies. Okay. يعني نحن على initial state كان عندنا بس elastic energy لأنه كان عندنا ال B elastic equal to half K delta square. Delta heat compression هن عطيونا إياها. It's given. So initially we know the elastic energy. وinitially كان السيستم at rest، يعني كنا حاطين البول على السبرينج مهدينا، كانت V equal 0. هلا بالنسبة للgravitational potential كمان you can take a reference wherever you want. هلا it's good to take it here لأنه هي initial position. يعني V gravitational at initial state at state 1 is 0. And since the only forces acting on your ball هن عنا هون spring force، عنا الويت، وعنا التنشن. Tension of the cable will not produce any work at any location لأنه as you can see your ball will move on a circular path and the tension is along the radius, so it will always be perpendicular to motion. يعني no work for the tension. And since the other forces اللي هن spring, will, weight are conservative, so we can apply conservation of mechanical energy. Between من initial state لstates اللي بيهمونا، نحن بيهمنا state B, what will happen at B and what will happen at C. So first, from A to B, at A we just have elastic energy. No kinetic, no gravitational, لأنه اثنيناتهم zero. Now, at B what will happen? Once we reach B, أول شيء الspring صار unstretched، ما بقى في أصلاً contact between the spring and the ball. يعني ما بقى في elastic energy. يعني V elastic at B is 0. What are the types of energy at B? تحولت elastic energy to potential energy plus kinetic energy. To get the potential energy, we are above the reference, يعني positive potential. We are above the reference by this distance, which is small r. So this is mgr is the potential gravitational energy. The kinetic energy at B هي half mdv square. So in this relation, the only unknown is vb. So you can get what is the velocity at point B. Now, they asked also not for only the velocity, they asked for the tension in the cord at B and C. يعني طلبوا the velocity at B and C and the tension at B and C. To get the tension, always when you are asked for a force, you should think about Newton law. So at point B, I want to apply Newton law. And since my ball is moving on a circle, I should think of using normal tangential coordinates. So as usual, ut is tangent to the path and un is directed towards the center of curvature. So this is un. Then in this case, what is my radius of curvature? I am moving on a circle of radius r. So if I want to find the tension at B, I will put my forces. The forces acting on my ball are the weight and the tension T. Okay. Therefore, along UN, the only projection will be the projection of the tension. So my equation is very simple. Tension at B is equal to the mass of the ball, m, times an, which is vb squared, over the radius of curvature at B, over rho at B. What is the radius of curvature at B? It's equal to small r, which is the radius of this circle. So I will replace rho B by small r. Now what will change from B to C? When you are at this position, طلعوا هون الكيبل تبعنا is like this. يعني كانت أول شيء formed of two parts. وكانت ال oscillating part is only the vertical part, this one. كانت عم تعمل rotation. Now once you reach B, you will have your cord. Your cord will be of length 2r. Okay? يعني from now on كل الكورد رح تبرم. يعني from B to C you are moving on a circle of different radius هو equal to this distance اللي هي 2 times r. So now the radius of curvature is was changed from r to 2r. So when I want to do analysis at C to find my tension at C, I should draw also the free body diagram at C. At C I have So let us represent the UT UN at T. This is UT, always tangent to the path. This is UN directed towards the center of curvature. Now concerning the forces, I have, so this is UT, this is UN. At this position, هيكون عندي both weight and tension along the vertical. So this is W and this is T at point C. This is T at C. Okay, so in order to get TC, I will write that sum of forces along UN at point C is equal to M times AC normal, and I can replace AC normal by VC square over rho at C, so it's equal to big M times VC square over rho at C. And since the radius of curvature at C is known, it's 2r, I can just replace it by 2r. The projection of forces along UN will give me plus TC plus W, because both are along positive UN. So plus TC plus W equals to mvc square over 2r. So now to get TC, I just need to get the value of velocity at point C. To get the velocity at point C, I should apply or work and energy or conservation of mechanical energy. بما انه كتير عملنا conservation of mechanical energy today, let us use work and energy. If I want to apply the principle of work and energy from B towards C, I will say that the only force doing work هي الويت، لأنه tension always perpendicular to motion, no work. So I can write that the kinetic energy at B, TB, plus the work of the weight plus work of W equals to kinetic energy at C, TC. Already for B, I know the velocity. I calculated from previous step. So I can just replace TB by half M times VB squared. Concerning the weight, I can find the work of the weight as mg delta y. So you know that the work of the weight is given by minus mg delta y if I consider y positive upward. Okay, so if I take here, this is y-axis, positive upward, then the work of the weight will be minus mg delta y equals to the final kinetic energy at C, which is half m times vc squared. Now what is delta y here? Delta y is y of C minus y of B. So as you can see in the figure, delta y is equal to this distance, which is 2r. Okay, so you will get half mvb square minus mg times 2r equals to half mvc square. So you can get the value of vc. I want to show you here that if you use the conservation of mechanical energy, you will go back to the same result. Why? Because if you write conservation of mechanical energy, you have TB plus V gravitational at B equals to TC plus V gravitational at C. If we consider that the datum is at A, if we keep it at A, we can do it. Then the potential energy at B, gravitational energy at B is VGB is plus mg times the small r, plus mg times the small r. While for point C, as you can see, the height from A towards C is r plus 2r is 3r. So this is equal to TC plus 3mgr. So now just take this term to the other side. If you take 3mgr to the other side, you will get mgr minus 3mgr. You will go back to minus mg times 2r. So both methods, of course, will give you the same result. And also you can change the reference. يعني you can take, instead of datum at A, you can say for this second calculation, I want to take the datum at B. So V at B will be 0, while V at C will be 2 mgr then. And again, delta will be the same. So if you put the reference at B, then V gravitational B will be 0. And V gravitational at C, instead of 3, will be 2 mgr. But at the end, the difference is the same, because 3 minus 1 is equal to 2 minus 0. So whatever is your reference, you will get the same result at the end. Okay? Any question on this?
دكتور
Yes.
بس لا اخذنا يو تي على اليمين.
ليش أخذنا UT what؟
على اليمين.
Okay. لأنه look, how you are moving from B to C, مش along this path, this is your positive direction of motion. بس توصل على C, كيف حتكون ال velocity؟ Like this, صح؟ يعني
كده.
أنت تخيل you are moving on a circle from B to C، على C حتكون velocity tangent to the path towards the right. فإذا UT كمان هي unit vector لل V بتكون towards the right. Okay?
Okay, doctor, merci.
Okay. Any other question on this? Okay. So if next time, if you have any questions for the exam, let me know, okay? Yeah, let's see you next time. I will post the recording, okay? Bye-bye.
Thank you, doctor.
Thank you,
Bye.
doctor. Have a nice day.
You too, bye.